All right, we're in the home stretch. We've got a couple more sections of Chapter 7, and we'll have this section all wrapped up for our third exam. This section is on, as it's titled here, ionic activity. And I say when you first learned about the concept of activity just a few days ago, it was said that it's sort of an effective concentration. That is, it's a factor that represents what concentration the solution is behaving like. Not the actual molarity or molality, but like a usually lesser molality. The activity coefficient, that was the little gamma term. Should put my little pencil on here. The little gamma term is the activity coefficient. That's the way to express how close or how far the solution is behaving compared to some ideal. And if you remember that longish problem I had asked you to do with the plot, all of a sudden blanking on which one that was. It's an important one to study. 619. On problem 619, when we were looking at non-electrolyte solutions, we saw that we could represent the activity or the activity coefficient in terms of a Henry's law as the standard or the pure vapor pressure as the standard. So double check that one to see what we mean here. But anyway, when we put an electrolyte into a solution, just like the cations and the anions contribute to the conductance independently, so they also contribute to the chemical potential independently. This is a bit of a theoretical part, but I think it makes some sense. So in solution, what we're saying is that the chemical potential of the solute, in this case an electrolyte, is really the sum of the chemical potential of the cation and the chemical potential of the anion added to each other. Now, in general, salts aren't always plus 1 minus 1. If you have salts that have coefficients, well, then you need to have that coefficient multiply times whatever the concentration is of that cation or anion. So the chemical potential is better represented as 715 in a more general sense. Now, again, I said, although this is theoretical, the chemical potential of each ion independently can be written as some standard plus a term that's dependent on its concentration. Just a little bit of a note here. The textbook writes molalities in this section as unitless numbers. They divide them by the unit, so 1 molal, just to get rid of the units. There's a couple of times in physical chemistry when they do things just to get rid of units, and this is one of those times. So really the point of this section in red is to remind you that the chemical potential of some constituent is going to be related to its whatever its concentration is. And because electrolyte solutions, let's say calcium chloride, are going to give different numbers for different ions, you need to take the molality of the calcium chloride and multiply it by 1 for calcium or for 2 for chloride. So the chloride's contribution will be twice whatever the molality of the whole salt is. And that is summed down below. Now, as I have here this theoretical expression 716 that sort of breaks apart constituent chemical potentials as being separate from each other. Now we know you can't study anions or cations independently from one another in solution. You can't just sprinkle in some sodiums into water and not have the chlorides along for the ride or whatever your counter ion is. Well, p-chemists are clever, and they've cleverly come up with ways to determine the quantity of the ions kind of as a group, and then we'll separate out the constituent parts. So we're going to define something called the mean ionic molality. And by the way, this is an example of what our friends in math called a geometric mean. It's a more accurate representation of what an average property is. You use arithmetic means, the kind of mean that you learned a long time ago when you think you have a random distribution of things. But in a geometric mean, for example, I gave the example of calcium chloride a little bit earlier. So there are twice as many, 2 times as many chlorides as there are calcium ions. So the randomness is not, what should I say, not the randomness, the distribution of the different charges in the solution is not random. There are twice as many minus ones as there are plus twos. And so math shows us in those non-random distributions that the geometric mean is better. And so that's what you're seeing here. So this mean ionic molality can get a little confusing the first time you look at it, but really it's a representation of how many of the ions of each type are contributing to the whole. And so the letter, it's really a nu, but I'll say V here, is the sum of the two coefficients of each. So in my example before, I said that the calcium was a plus 2. There was only one of them. So the V plus for calcium chloride would be a 1, and the chloride would be a 2. So you need to apply those into the equations as shown. So whatever the molality of the solution is can really be brought out, and then all the coefficients are inside the bracketed term. So I have an example down here below. I sort of forgot about, but it's right here. So for magnesium phosphate, let's express the chemical potential in terms of the molality of whatever that salt is. And so there are 3 magnesiums floating around for every 2 phosphates. The total number of ions in solution then is going to be 5 times whatever the molality is. The mean ionic molality then is going to, you pull out the molality out front, and then the coefficients are inside here. So the V plus to the V is going to be 3 to the third right here, and then 2 squared, and then raised to the 1/5 power gives a net of 2.55 times the molality. So that's what the mean ionic molality is. This is the representation of equation 716 that we had way at the top. The standard chemical potential in this case for this salt solution is going to be the sum of the contributions from the cations and the anions. But we're focused more on how to calculate these new sort of concentration-ish terms that we're learning. So unlike non-electrolyte solutions that we did Raoult's law for, or Henry's law in chapter 6, most electrolyte solutions behave non-ideally quite quickly. The intermolecular forces are the reason why. So if you have, whoops, I made a little typo here. If you have a intermolecular force, let's say, ion dipole or London dispersion forces, not ion dipole because that is Coulomb's law, but a non-Coulomb's law force like a London dispersion force, the power drops off very quickly. It's to the power of 1 over r to the 7th. Coulomb's law, as we saw earlier in this chapter, is 1 over r squared. So kind of a rule of thumb for non-electrolyte solutions, anything about 0.1 molal or less is essentially ideal. You don't see a big deviation from Raoult's law or Henry's law. For electrolyte solutions, even molalities less than 0.05 molal show deviations, which means that you don't use molalities if you're trying to find the properties of solutions. You have to use activities, just like we did in the last chapter. So colligative properties, for example, which we did molalities, or in the case of osmotic pressure, molarities. Toward the end of this chapter, we'll do it in terms of activities. So by analogy, the mean ionic molality from the previous page, we're going to do mean ionic activity. And the mean ionic activity is represented, do I have an equation number here? Sorry about that. You can see it in your text. Whoops, forgot an equal sign there. Wrote that a little too fast. That's 7.20. This is 7.21, and this is 7.22. So the mean ionic activity is going to be a term that takes the activity of each ion raised to its power, how many there are of each, and using the definition of the activity coefficient, these can be combined. Let's take a look in. So there's figure 7.8 here shows you the deviation from ideal for a variety of electrolytes at a really, really low concentration. The activity coefficient, I should say the mean ionic activity coefficient approaches 1, and as the concentration gets bigger, you can deviate quite a bit. Let me write down those terms again. Again, the A plus minus, that's the mean ionic activity. M plus or minus is the mean ionic molality. And gamma plus minus is the mean ionic activity coefficient. So I reproduced a couple of equations before. I'm not sure why a couple of these have different forms, but I'll use these forms to solve this example. So this is example 7.8. They're asking to write expressions for the activity for a variety of salt solutions in terms of their molality and their activity coefficient. Remember, the idea again is the activity coefficient can be measured experimentally, and if you know how concentrated your solution is, you can get the activity from that. Anyway, starting at the beginning, for the easy salt potassium chloride, the V plus number is 1, the V minus value is 1, and so the V value, that's V minus, is 2. So my mean ionic molality is going to be whatever the molality of potassium is raised to the first power times the molality of the chloride raised to the first power, so that ends up being molality squared, raised to the 1/2 power because V is 2. So M squared raised to the 1/2 power is M. So for the activity, I'm just going to plug in M for the mean ionic molality, and then times whatever the ionic activity coefficient is squared. Of course, that makes sense if basically this is saying that the average molality of each charged particle is whatever the molality is. So here we have sodium chromate. The V plus is a 2, the V minus is a 1, and the V is a 3. So the first term, again, I'm looking up at the top here. The first term is the M plus term. So that's the molality of the sodium is going to be 2 times whatever the molality of the salt is raised to the second power. And then I'm going to have the molality of the chromate is M raised to the first power, because there's only one of those. And if you multiply that through, looks like I got 4M to the third here. And so taking the cubed root, I have the cube root of 4 times M is equal to the mean ionic molality. Then when the M plus goes into the expression for A, and that's raised to the third power goes away for the 4, and it becomes M cubed, gamma plus minus cubed. And then finally, when the V plus is a 2 and the V minus is a 3 and V is a 5, you could work through that and get 108 M to the 5th gamma plus minus to the 5th. This certainly suggests that you're going to get some wide deviation from any kind of ideal behavior when you have ions with these charges in it. I haven't done these yet, but if you can, before class, look through this section of the book and give these problems a try. This could be what we cover on Monday. See you then. Bye-bye.